make sure my pen works. All right, my pen does work, so we're in good shape. All right, well, welcome to, I guess this is AE 566, electric propulsion. If you think that's the wrong class, it's time to get up and go, or you can stick around if you want. I posted a syllabus on, is that focused? Yeah. On Canvas, and it gives basically the course description, the textbook, which is nice and cheap, from Dover. It's the first book on electric propulsion, and really the only one that stands up to the standard of time. Even newer books aren't as good as this one. So it's kind of a fun thing to have in your library. In this course, we will cover applications of electric propulsion. And by electric propulsion, I mean space or rocket propulsion, not electric powered vehicles like airplanes, or I had somebody wanting to know about cars, hybrid cars at one point. That is not a part of this class. Electric propulsion devices deal with plasmas, the fourth state of nature. So we will have to learn a little bit of background about electromagnetic theory, ionization in gases to make the plasma that's used in these devices. We'll look at particle collisions, development of methods for measuring the electrical conductivity or resistivity of the plasma, which becomes important for the application of power to these devices. And that will probably take us through midterm. And beyond that, we will use what we learned in the first half of class to look at specific types of EP devices that fall into three categories: electrothermal devices, electrostatic devices. Electrothermal devices are like arc jets, if you've heard of those. Electrostatic devices would be ion engines. I always make the joke about TIE fighters and Star Wars twin ion engine. Anyway, let's see, then electromagnetic accelerators, like hydrodynamic systems. And if I have time, we will discuss solar sails. The Planetary Society recently launched a satellite called LightSail 2 that is the first device to demonstrate in orbit the propulsion aspects of solar sails. And we might touch a little bit on nuclear propulsion as well, since that's becoming a hot topic these days. Okay, in this class, grades will be determined from what I'll call projects and homework, 30% there, 30% for midterm exam, and 30% for the final exam, or 40, excuse me, for the final exam. Tests are typically in class, open book, open note kind of thing. And homework and projects. Homework will be basic homework problems that I either make up or sign out of the textbook, and projects we'll probably end up doing one or two reports where everybody's assigned a specific thruster and does a short paper on it that gets shared with the rest of the class. Because there are a lot of specific devices out there that we won't have time to cover in great detail in lecture. Grading. I use the scale posted here. I do reserve the right to curve grades, but curving the grades will never harm you. It can only improve your grade. And I do that at the end of the semester, not after like an exam. Let's see. This bottom statement, I've been told I have to put that there. I've never had to change the syllabus, but if something arises and it looks like we have to alter from the syllabus, I will post an update and let you know if that ever happens. Anybody have any questions? Okay, I like to have a very informal class. So if you have any questions, I'll answer to hey you. I might even answer to hey idiot as long as you say it nicely. I make mistakes, so correct me if you think something weird's happening. You probably hear at least one stupid, corny joke a day. You don't have to laugh. I'll laugh at myself. All right, so electric propulsion. Everybody's seen rocket launches, Space Shuttle, SLS, the Falcon rockets from SpaceX. Those are all chemical rocket systems, high thrust. They don't utilize propellant very well, so they're not especially attractive for use on deep space probes, satellite station keeping and maneuvering. And for that, you want a more advanced technology, and electric propulsion systems offer that. Many systems are commonplace today, and we've been developing electric propulsion systems since the 1960s. Okay, and it's gone through this, we're going to get there in 20 years thing like hypersonics did for a long time. Well, in the 1990s, it really came to fruition for electric propulsion. Just to give you an idea of what industry thinks of EP devices, this is a plot of the number of COMSATs in geosynchronous orbit from 95 through 2010. I didn't happen to find anything that's more recent than this. But this plot, if you go back to the 60s, takes on an exponential growth and it is continuing. These are very reliable systems and are being adopted by all major satellite manufacturers and the Department of Defense and NASA. I'm not going to spend a whole lot of time on this. This shows the number of satellites as of, I think it was 2008, in low Earth orbit or geosynchronous orbit that have electric propulsion rockets on them. And as of 2008, there were 226 satellites that used EP systems. That does not include the number that have been decommissioned and deorbited. And right now, ArcJet technology, we'll learn about later, takes up the vast majority of those. That is not because it's the best option. That is because it's basically one of the earliest to come online. And so it was adopted, shown to be very robust. So people aren't quick to adopt new technologies until they're fully checked out. Okay. Just to get us started and whet our appetites, let's look at thrust and specific. I'm not going to talk about specific power, thrust and specific impulse. Okay, so the thrust for a rocket motor. Is obtained by integrating the momentum flux over the nozzle area. So we have thrust is equal to the integral of the area of the nozzle, and this would be like a traditional chemical or thermal device. And our momentum flux is rho times u squared, and then we could have a pressure acting at the nozzle exit depending on the local conditions, dA. In space, this rho u squared term is typically much greater than the pressure term, so we tend to drop that, ignore it. So thrust is equal to the integral of rho u squared dA. And if we assume a uniform flow and velocity distribution, this is just equal to the mass flow rate of the propellant times the exit velocity. All right, so in most cases, you want a higher thrust because you can move around faster. If we think about being in space, okay? There is another measurement of performance called specific impulse, and we'll go into these in more detail later. I'm just kind of giving you a brief introduction now. The specific impulse is the ratio of the thrust to the unit weight flow rate of the propellant. This is typically written as I sub SP or specific impulse. And your book by Robert John, that is written I sub S. That's the one place I've seen it routinely used that way. So we'll switch back and forth a lot. You'll hear me say ISP a lot and write down I sub S. Okay, so our specific impulse is equal to thrust divided by, I'll just call it W dot, which is the weight flow rate. So this is equal to the mass flow rate of the propellant times the exit velocity, assuming the uniform distributions of each across the nozzle, divided by the mass flow rate of the propellant. Notice that's the same as it is in the numerator, times Earth's gravitational constant. This is just how it's defined. So the mass flow rate drops out of the equation, and we have that specific impulse is equal to the exit velocity of the propellant from the nozzle or accelerator divided by the gravitational constant. And this is an easy thing to deal with in MKS units, because if you need to know an ISP, you know the exit velocity or vice versa with a factor of roughly 10, 9.8 meters per second squared. Okay, the last thing I want to write down is the relationship that thrust is equal to m dot times u exit. If we solve for u exit in the prior equation and plug that in, we have m dot times the gravitational constant times the specific impulse. So for the same flow rate of propellant, the higher your specific impulse, the higher your thrust goes up. Right? So you want to have a higher ISP. The converse of that is, if you're looking for the same thrust level, if you have a higher ISP, you have a lower mass flow rate, which means you use less propellant for the same mission. Okay, so there's benefits for using the higher specific impulse. And There's also some drawbacks to it. We'll talk about those later. But the bottom line is that it is really expensive to launch mass into orbit. And if you can minimize how much propellant you take with this or with you, you can increase the amount of payload that you take up. So you can launch bigger or more sophisticated satellites or more of them on the same launch vehicle if you go with a high ISP propulsion system. So it becomes very attractive for telecommunication industry as well as Department of Defense and anybody that's putting assets up in orbit. Any questions about that? That's just kind of a background as to why we want to use these things. Now, just to give you a feel for specific impulse, I've got a chart here, something else that I pulled off of the internet. Good, it's showing up. Okay, so here we have specific impulse. This 1/seconds is wrong. Specific impulse comes to us in units of seconds. But specific impulse is a function of thrust. And as you can see, the chemical rockets are down here with a low ISP and have a relatively high thrust associated with them. Their ISP, Space Shuttle main engine, is probably one of the best, if not was the best, highest performing chemical rocket produced. And it's at about 450 seconds of ISP. Okay, then if we want to go to higher ISPs, we've got a nuclear thermal propulsion, which I'll introduce later. What that does is it gives you a boost in ISP up to about 900 seconds. And you take a hit for the maximum thrust that's practical out of those devices. The electrothermal, electrostatic, and electromagnetic written on here are forms of electric propulsion. All of these things can be powered by a nuclear generator, a reactor. But for practical purposes, they predominantly use solar arrays, especially for low Earth orbit and GEO. But you can see here that thrust levels on electrostatic systems, and these would be used on regular, normal sized satellites, are on the order of 1 millinewton of thrust compared to a chemical system that could be a newton or a quarter newton. That would be very small. But notice that on the specific impulse scale, on electrothermal systems, you can get upwards of close to 1100 seconds. Electromagnetic systems will go up to 11,000, and electrostatic systems can go practically up to tens of thousands of seconds. And there are reasons why you select different ISP ranges that we'll get to later. But my main point for showing this is that these things operate in a completely different regime than a conventional chemical system. All right. This thing can only focus when I put my hand in here to start with. So let's just talk a little bit about history before we get into the technical stuff. All right, so if we look back into the 50s and 60s when EP was a baby, there were lots of things being developed. For most of the 50 years since the publication of our textbook. Of John, which was published in 1968. EP has been described as a technology with great or tremendous potential. And at least initially on, I think, researchers use words like this to get funding. Right? Okay. That's an attempt to be funny. And that potential is to reduce launch costs. Extend satellite lifetime. And provide a means to explore the solar system. You've probably heard of like the Dawn mission that went out to beyond the asteroid belt up towards Jupiter and studying various celestial objects and it had ion engines on. So those weren't used for station keeping; they were used to basically change the orbit, and would run for hundreds and hundreds of hours nonstop in doing so. All right, where did it begin? Significant electric propulsion research programs were established in the 60s. At NASA, Hughes Research Laboratories, any of you heard of Hughes Aerospace Corporation? That's before your time, but it got assimilated into other companies. There were others too, Aerojet. And those were all in the United States. There was also a lot of activity in various institutes in Russia. Okay, arc jets. An arc jet is a device that uses an electric arc to heat up a propellant to temperatures much higher than you can achieve through chemical energy release and chemical reactions. Arc jets have been were in development from the 1960s to the 1970s. Okay. ArcJet first saw its first launch on a satellite in the 90s. called Telstar 4. And that was a communications satellite. Basically, in the 90s, it's not like, oh, we abandoned ARC jets. The government and agencies around the world kind of developed that the technology was mature enough that it could be used in widespread use on satellites, and that's why that chart I showed you gives such a large fraction of ARC jets on it. Okay. Another EP technology. That was developed in the US. In the 60s. Continued in the USSR. Or basically Russia. This was the Hall effect thruster. And it was in wide use in the USSR on their Meteor satellites. And this is now considered, these Hall thrusters are now considered one of the most promising EP technologies. I was in graduate school when the Iron Curtain fell, and there were a bunch of starving rocket scientists in Russia wanting to sell their wares. So the United States and the free world, the West, was flooded with these Hall thrusters that the United States had given up developing by the early 70s. And the Hall thrusters that Russia had produced at that time outperformed our ARC jets, and they still had lots of problems. And ultimately what happened is that our government here in the United States recognized the potential of these things and worked with these newly available scientists to optimize these systems. And now they're basically mature and they're being used as much, if not more, than ARC jets. So why would we give up on the Hall thruster if it was so wonderful, right? We'll find out later in class it's a relatively complicated device. There's some complicated physics involved. And the USA largely or totally dropped Hall thruster development to concentrate on development of the the ion engine. And if you remember from that plot that I showed, the ion engine falls in this electrostatic realm in the top half, and the Hall thruster falls in the bottom half. So the decision was made by developers, Western developers, to go for the higher performing system. And as we'll find out later on, that in general, when you have a higher specific impulse, your thrust level goes down, which means it takes more time to complete a maneuver than a lower ISP, higher thrust system. And so sometimes it's more important to be able to move quickly than efficiently. An example is the Desert Shield. Everybody know Desert Shield? Desert Storm. We had the Desert Storm, which was the first war that we fought with Iraq after they invaded Kuwait. So during Desert Storm, that region of the globe was a hotbed, and our military leaders were very resistant to adopting electric propulsion because of the lower thrust levels, because they wanted to be able to move their spy satellites from point A to point B quickly, not have to wait forever. So things like that caused delays in adoption of electric propulsion, which ultimately has been used now. And when I get to talking about arc jets, I can explain how researchers and engineers sold the government on adopting arc jets first, because they could be operated in a less efficient, higher thrust mode. So it's like a transition, stepping stone. So this class isn't about history, and it's not about politics and all that kind of stuff, but when it comes to the development of rocket technologies, it's hard to separate the two. All right. So Russia was the first to adopt electric propulsion in wide use through their Hall thrusters on the Meteor satellites. My data is old, so I'm not even going to talk about it, but there are now hundreds of satellites that have used electric propulsion systems, and that number is growing exponentially. And it's not just in use by the United States and Russia anymore. All spacefaring nations are adopting these things. All right, any questions, comments? Let's get to some more technical stuff. In John's book, the second section is called High Impulse Space Missions. Okay, so we have two principal factors. Oh, and by the way, if my handwriting gets too sloppy to read, get my attention, tell me to slow down, stop drinking so much coffee, whatever you need to do so that you can read my handwriting. I won't get upset. I know it's horrid. I do the best I can. So we have two principal factors that influence the choice of propulsion for space missions. Okay, one of those is the thrust produced per unit mass of propellant. And the second one is the power required to produce that thrust. Okay, we've already talked about a little bit about the first one with that, the ISP, right? Specific impulse. So the specific impulse IS, as it's denoted in our textbook, measures the first of these. It is defined as the thrust divided by the weight flow of propellant. And say at Earth's sea level gravity. The parameter used to describe the second is propulsive efficiency. And that is the ratio of input power to thrust power. Okay, so for most of the history of spaceflight, thrust has been produced by chemical rockets. Okay, and here in these devices, combustion provides the power source. And thermal expansion in the nozzle produces the thrust. Okay, so in a chemical rocket, the specific impulse is determined by the speed of sound in the propellant gas. Okay, and the power by the energy released by the combustion. So the power available, excuse me, oops, can't spell today. The power available, and that would be the combustion power, available is proportional to the mass flow rate. Right, you can only get so much energy out of a chemical reaction, and you want as high a temperature as you can, and that leads to thermal expansion in the nozzle that accelerates the flow and reduces the thrust. With electric propulsion, the power available by the system is determined by system considerations. Typically, the area of solar cells carried by the satellite. Solar cells. Can't spell satellite either. Okay, so traditionally that's been about 30 kilowatts on orbit, especially low Earth orbit. It's not much power. And so that's been pretty limited. We are developing better solar cell technology all the time, and that's going up, but not that quickly. So this is still a limiting factor. Other sources such as nuclear. Like nuclear fission have been proposed. But not employed. Now, having gone that far with it, there have been times over the decades where they were being nuclear reactors for space use were being developed. The first, the most widely known, is a project that developed from the Kiva program, which transferred into the Rover program, which transferred into something called NERVA, which you may have heard of. NERVA is like nuclear electric rocket, something or other. I forget the rest of the acronym. The NERVA program went on for most of the 60s, early into the 70s, and we had up to gigawatt level reactors producing tens of thousands of pounds of thrust, operating out in the middle of the nuclear test area out in Nevada. it was a demonstrated technology and fell out of political favor. And so that technology was largely lost. It's written in the history books and some reports that we lost the ability to do that. That was a nuclear thermal system where the nuclear reactor was using hydrogen as a propellant. And that hydrogen was the coolant for the nuclear reactor. It was heated up to very high temperatures, much, much higher than you can achieve in a chemical reaction. And then that hot hydrogen was just expanded out a nozzle. Very simple device. Then, because of the concern associated with, engineering problems with the materials and the potential release of nuclear materials, things started to shift more into using nuclear reactors, fission reactors, to provide electrical power for standard electrical systems. Back during the George Herbert Walker Bush administration, there was a proposal for a system called Prometheus, which was a demonstration to go to Jupiter's icy moons, and it was going to involve nuclear electric propulsion and development of space-weight reactors. Continued again until it got killed. And more recently, with our current administration, it has now become a high priority for taking people to Mars. And so normal conventional chemical rockets that produce enough thrust to do it, because of their low specific impulse, cannot get people there fast enough. And so they're exposed to too much solar radiation, and we can send people there, and we might even bring them back, but they're going to die of cancer or whatever happens when you get exposed to too much radiation. So NASA has turned to nuclear thermal propulsion once again as the only practical way to get people from Earth orbit to Mars in a short enough period that they're not exposed to detrimental levels of radiation. And in fact, nuclear thermal propulsion divides the trip time by a factor of almost 4. So it's a big deal. It's not just a matter of, oh, we're going to shave off a couple of weeks, shave months and months off of it. So there's a big push for that to happen now within the government, and it'll be interesting to see if political opinion ultimately is supportive of that or not. But I think that engineers have proven that they can design these things safely enough that even in the event of a catastrophic failure on the launch, that all materials can be contained. So I'll get off my soapbox there, and because I'd like to see that happen, although I'm just a rocket junkie. So anytime we can do something new, I'm happy to see it happen. All right, back to this. Okay, so by going to these alternate energy sources, we're divorcing the thrust from the power or the heat, right, that you have to have with a chemical system. So the separation of the power source from the mass flow rate provides the flexibility in the design of EP thrusters. which can provide much higher specific impulse. Then chemical rockets. Okay, the basic equation of motion for a rocket. And this would be any kind of rocket that is in a gravitational field. Is mass of the rocket times its acceleration vector is, oops, there is no dot there. M times v vector dot is equal to the mass flow rate of the propellant times its exit velocity vector. That would be the thrust, with minimal contribution from the pressure term, plus a gravitational force vector. This is equation 1-1 in your textbook. So here, M is the mass of the rocket. The v vector is the rocket velocity. UE is the velocity of the exhaust gases. And F vector is the local gravitational force. And I just lost my microphone. My bad.
We can't have nice things.
We can't have nice things. I know, I keep trying to break stuff. Sorry about that. I hope it didn't make a loud crack in people's ears. Bam! Okay, gravity. We talk about gravity and we had to have a demonstration. Okay, so F sub G vector is the gravitational force, and we didn't define M dot, and that is the propellant mass flow. Because it doesn't have to be gaseous, you can have somebody on the back of your rocket throwing off pieces of it to acceleration. Okay. The term involving the mass flow rate, M dot, is the thrust. So the thrust vector is equal to M dot times the velocity vector. This is equation 1-2. The integral of the thrust over time. over the time the rocket is running or fired is the impulse. And so we'll write that as capital I is equal to the integral from some initial time t naught to some final time t sub f of thrust v times dt, and that's equal to the integral over the same time period of m dot times u e dt. That's equation 3. For the same impulse, the quantity of propellant that must be carried let's see, for the same impulse, okay, for this quantity, the quantity of propellant that must be carried is lower or higher exhaust velocities. And so that's where we get higher ISP, which is just directly proportional to that exhaust velocity. Okay, if the rocket operates with constant exhaust velocity, then our equation of motion, which is equation 1-1, integrates to delta V is equal to the exit velocity times the natural log of the initial mass divided by the initial mass minus some delta M, change in mass. Okay, so here we have M naught is the total initial mass. And propellant. Okay, the ratio of initial to final mass determines the maximum velocity of the rocket. So the change in the velocity vector that is maximum is equal to the exit velocity out of the rocket times the natural log of the initial mass divided by the final mass, where the final mass is just the initial mass minus the delta M used in the propellant. Okay, this is equation 1.5. The useful final mass of the rocket is given by final mass divided by initial mass is equal to E raised to minus delta V over U sub E. I forgot to mark equation 4 up there. Equations 4, 5, and 6 are commonly referred to as one form or another of the rocket equation. Okay, so if we look at equation 6, we can say that the exit velocity U sub E should be comparable to the delta V if a significant payload remains after the rocket propellant is expended. Okay, let's see. More complex missions can also be analyzed and a characteristic delta V developed for the mission. Some examples are shown in table 1-1. Which is on page 4 of the textbook. Put these here, and I'll get to play with Zoom for the first time. Cool. This is the new system from what I used the last time I taught in this room. Okay, so we have here a list of missions, and they're given in increments of a lot or delta V's, meters per second. So if we look at escape from the Earth's surface using an impulsive delivery system where basically you turn on high thrust and then once that's done, coast. That is over 1,100 seconds. If you escape from a low Earth orbit, that is just over 3,000 meters per second. They have a gentle spiral here instead of impulses that requires even more delta V. Okay. And we'll see later on that makes sense for a high specific impulse EP thruster. And they have Earth orbit to Mars orbit and then various solar system missions given. And so if you look at going from Earth orbit to Saturn orbit and a return, that's 100,000 meter per second delta V. And so you can use those numbers in the rocket equation to get a feel for the, cool, we had fun with this. Okay. To get a feel for what your payload fraction will be. And note, this M naught over MF isn't payload fraction, that's what's delivered. So you have structure in there, tankage, engines, pumps, things like that, plus the payload. So that all comes out of this M final. Any questions about that? I hope you're as excited about this stuff as I am. I want to keep going, but we're running out of time. Let's get started on the next section from the book. Exhaust velocity and specific impulse. Okay, so by definition, as we wrote early, that the specific impulse is the thrust, m dot times uv, over the weight flow rate of the propellant, or in simplistic terms, that's UE over gravitational constant. In MKS units, the gravitational constant is 9.81 something or other meters per second squared, about a factor of 10. Typical values. Of the specific impulse. Chemical rockets. Monopropellants, solid rocket motors can be dogs compared to liquid rockets. So we'll have a range of about 200 to 440 seconds of ISP. Now there are some hypergolic combustion systems that can achieve much higher ISP than this, upwards of 550 seconds, but they're very dangerous and hard to deal with and aren't in practical use. So that means that for chemical rockets, we have about 2,000 to 4,400 meter per second exit velocity. Okay, if we look at that, well, here, I'll do that in a second. Let's look at nuclear rocket, nuclear thermal. They can go from anywhere up to about 900 seconds. So that would be about 9,000 meter per second UE. Now let's look at the EP systems. Electric propulsion. We'll do the lowest performing of those, which is electrothermal. And an example is the arc jet. And ones that are typically in use are 500 to 600 seconds. You can get higher than that, but there's reasons why people don't, which we'll talk about later. And again, so this would be 5,000 to 6,000 meters per second exit velocity. Then we have electrostatic devices like the ion engine. So this would be electrothermal, electrostatic. Ion engines will be on the order of 3,000 and can go really high, 10,000 seconds. So we have 30,000 to 100,000 meters per second on those. And let's do Hall thrusters, Hall effect thrusters. And you can see people argue about this and debate about it. General consensus are that these are electrostatic devices, but there are people that will argue that they're electromagnetic devices, and we'll get to that also later. But these are on the order of 2,000 to maybe 3,500 second ISP, which is 20,000 to 35,000 meters per second, roughly. And if we look back at table 1 on page 4, we see that a lot of these missions are in the anywhere from a couple of them at 3,000 to 8,000 meters per second, but the vast majority are at least 10,000 meters per second on the delta V. And so if you want to have a practical payload mass, you need to have the delta V over UE term in the rocket equation be higher, right? So you want to go to a higher ISP to increase your mass fraction, which will get you more payload to your destination. So that is what drives people to head this direction when it comes to delivering payload to anywhere other than like low Earth orbit. Going from LEO to geosynchronous orbit, it takes quite a delta V, so EP divides for that as well. All right, this is a good stopping point. Anybody have any questions before we go? Please start reading that first chapter. The next time we'll probably finish up chapter 1, and I will give you some problems to start practicing with. I did forget to mention at the beginning of class when I was talking about syllabus on homework, I do not grade, do not put a numerical or letter grade on your homework. I correct it. I use it as a diagnostic tool to make sure that you understand what you're learning in class. And also it takes the pressure off of you on the homework. I want you to put in a valid effort and demonstrate to me that you have tried to understand the material. But if you have a problem with the homework and that can't be resolved with a brief discussion by us or a sit down talk, we can always cover things in class. Okay. All right, that's all I've got for today. Start reading that chapter, and I'll see you on Tuesday.